Hello, my name is Yanofsky. We're doing analysis of algorithms. We're up to chapter 22, elementary graph algorithms. And what this is all about is doing basic simple things with graphs. Okay, so let's talk a little bit about how you represent a graph. You've seen this all in your data structures class, so you've seen this before, but I just want to get the notation down pat. Okay, if you have a simple graph like this with 5 points, you can represent it as an adjacency list, where this is basically a list, an array of linked lists, and 1 is connected to 2 and 4, so that you have at position 1 you have a linked list of all the nodes you're connected to. 2 is connected to 3 and 1 and 3. 5 is connected to 3 and 4. Okay, so you have, this is an adjacency linked list. As opposed to that, this is an adjacency matrix. Okay, so 3 is connected to 2, 4, and 5. 3 is related to 2, 4, and 5. So if they're related, there's a 1 there. If they're not related, if there's no edge between them, there's a 0. Okay, so here are two simple ways. Obviously, you can't represent a graph with a picture in a computer, but you can represent it as an adjacency linked list and as an adjacency matrix. We're going to be able to go backwards and forwards between those two, and we're gonna do it fairly quickly. Okay, great. Now, section 2.2, 22.2. So that's section 22.1. Just shows you how these things do. And by the way, these graphs could be weighted graphs. And so you'd put the weights, how much the edges are, 13 or something like that. How much are these edges connecting the two? They could also be directed graphs, okay? And you're going to read in the book how they're doing. And you could put the weights, instead of putting 1, you can put a weight of the weight that's in there. So section 22.1 deals with all different types of graphs, directed graphs, weighted graphs, complete graphs, and shows how you can represent them. Okay, not a hard read, and again, you've seen it all in data structures before. Let's do section 22.2. Okay, 22.2. This is about 22.2. This is about breadth first search. Okay, breadth first search. Okay, let's just go through what this is all about. You know what a breadth first search is for a tree. You know how to do a breadth first search for a tree. You go father, then his children, then his grandchildren, then his great-grandchildren, etc., etc. Okay? As opposed to a depth first search, where you go all the way down to this. Now, you're going to have to be doing this both breadth first and depth first, both for trees, but here we're going to talk about doing it for a graph. Okay? So things get a little bit more complicated. I just want to explain to you why it gets more complicated, because you're going to have a graph of the form like this. Okay. Now if this node wasn't here, you'd say this was the father, this is the son, and this is the son. That's very good. And you could do a breadth first search. You do the father, the son, and the son, no problem. Okay, you could do a depth first search and do this first, then do this, then do that. Okay? But here we have this extra node. This makes it into a graph, not a tree. Okay? And so the question is, what is he? Is he a first generation or is he a second generation? Okay? Here's the father, here's the son, here's the grandson, or is he a son? Okay, and because of this screwed up notion, because they're in a graph in general, there is no thing, there's no concept of who's a father and who's a son. That works for a tree, not a graph. So we have a problem with that. Basically, when we do a breadth first search on a graph, what we do is we build a tree inside the graph. We build a tree inside the graph. And once you have a tree, you have a notion of what's the first generation, what's the second generation, what's the third generation. Okay? Now, the book the book goes through a lot of different information, and the book is very, very clear. Every single node has a color. There's a color to the node. And basically, the node, all the nodes start off as white, which means the algorithm hasn't seen it. Then it becomes gray, and in the book they make it gray, but here we don't have gray, so we're going to make it like that. And then it goes black. And we write it like that. Okay, so every node during this algorithm that does breadth first search is going to go every single node is going to go through these 3 stages. When everything is black, then we finish. Everything starts off as white. Okay, so that's one thing that they have to keep track of, is the color of the node, and you'll see why it's done. But the main point is that the algorithm keeps a lot of different information about the nodes, and we get a lot of different information. So given a graph, we get a lot of information, and we'll see later on what we actually do with this thing. Okay, another piece of information is the distance. So this is color of u is a node. Distance, this is the distance from the starting point. This is the distance from the starting point. So we write it as follows: d of u is equal to, I don't know, some number. Okay? Okay? And finally, the parent. Oh, but again, this is what we were talking about. Because there's a set distance from for each node, how far you are from the parent, the distance corresponds to what generation you're in. Okay? If your distance is 0, that means you are the parent. You are the root. Okay? If your distance is 1, then you're a child of the root. If your distance is 2, you're a grandchild of the root. Okay? Okay, next, we keep in track of the parent of u. Okay? In other words, who brought it into the tree? I told you we make this tree. Well, every node in a tree, except the root, has a father, a parent that brings it into the tree. Okay, and so we call that pi of u. Okay, so for every node, we're going to have to keep track of these 3 pieces of information: what's its color, what's its distance, what's its parent. Okay, and the idea is as follows: if you have a node u, okay, and you have a parent, then the thing that brings it in is called the parent of u. Okay, but things get a little bit more complicated here, because in a graph you could have 2 things going like that. So you have to choose which one is the parent. This is the parent or that's the parent. Same thing here. Who's the parent of this node? Him or him? Okay, and so we have to keep track of that. Okay. Now, the book does an example of an undirected. We do directed. You have to know both. Okay? I do it a little bit different in the book simply because I wanted you to see both. You'll see directed, you'll see undirected. Okay? And I can ask questions in either one. Great. Now, what I want to do is, I want to write the algorithm. The algorithm I'm going to write here, and here we're going to do an example of the algorithm. Okay? But you don't have to write the algorithm because it's on page 595. But it's helpful to write the algorithm a few times to get a feel for it. But it doesn't have to waste your time doing it while I write the algorithm. Okay, this is the algorithm, and as I told you, the algorithm is in the book. I didn't write it perfectly clear because you can look in the book. I just want to be able to point to it. And here's an example. We're going to go through the example very, very carefully, following what's in the book. Okay? The book does a different example. You should look at the book's example also, but you should also write this 2 or 3 times to get a feel for it. But let's do it the way we see it. Okay? I just want to say this is a little bit of, we're going to need this. You're going to have a vertex u, you're going to have a vertex v. U is going to be the child of it. So we change this, the parent of v is going to be u. And if the distance from anywhere from the starting point, s, till u is x, then the distance here is going to be x plus 1. It's going to be one further thing. So we're going to be updating the children in terms of the parent. Okay? Okay, so we don't need this. I just wanted to show you what's going on here. Again, I'm not going to read this to you because even if you can't read it, you can look it in the book. Okay, and it goes as follows. Okay, first we have to initialize everything. So everything for each vertex u in the graph, I'm using the 3rd edition's books, which is very much in the OOP version. So the graph dot vertices, everything except S. S is your starting point. So BFS, breadth first search, here's your graph, and here's your starting point. We're going to assume starting point is 1. Okay? So set all the colors to white. Notice all the colors are white. Set the distances to be infinite. In other words, what is the distance from all of these things, from all of these vertices to the starting point? Well, right now the tree doesn't exist. We're going to be building this tree. And set everybody's parent to be nil. Again, the parent is who brings you into the tree. We don't have a tree yet. Okay? Now, for S, so this is for everything except S. For S, make the color gray, so we do that. Make the distance equal to 0, so we do D equals 0. And make the parent is equal to nil. Parent is equal to nil. Okay? He is the root of our tree. The parent of the root is nil. Okay? Adam has no father. Okay. Now, here is a Q that we're going to use. This is going to be the starting point. This is the things are going to go in here and they're going to come out here. For a breadth first search, we use a Q. We're going to see in 20 minutes. For a depth first search, we use a stack. Okay, but the Q. So look what it says. Q is equal to empty, empty the Q, and then put on the starting point. So we put on 1, because 1 is the starting point. Okay, now we're up to here. This is the initialization. Now we go through the algorithm. Let's see. While U is equal to dq of U, so we're going to pull off 1. I'm going to pull that 1 off. Okay, and now we're going to look at what for each vertex member of G dot adjacency, the adjacencies of U. Tell me, who is next to U? So again, the graph, and then you have the adjacency of U. I don't care how the graph is given as a matrix or an adjacency, but this algorithm is just explaining. Graph dot adjacency of U. Okay. If so, let's go through it. He has 2 children, 2 and 4. 1 has 2 children, 2 and 4. Okay. We're going to do them in numerical order. 2 comes before 4. And for each one, here's what we do. If V color is equal to white, he's white. Then V color is equal to gray, gray. If V dot D, his distance is going to equal to U dot D, that's his distance, plus 1. So that's going to equal to 1. He's going to be the first place in our chart. Okay? And V dot parent, his parent, is equal to U. So parent is equal to 1. So he's the parent of this. Basically, this node is going to be in our tree. I'm sorry, this edge is going to be in our tree. Very good. Now, look what it says, and Q put on V. And Q put onto the Q V, child 2. So we put it on. Next, so we finished with this, but we still have another child, so let's do the other child. If color is white, the color is white, which means we didn't see it yet. You will see this later on when we do see a node. Okay, color is white, and then set the color gray. Distance is equal to his distance plus 1, so that's 1. And the parent is equal to 1. So this guy brought 2 children into the tree. Okay, put on the in Q, so we put on 4. Okay, go back to the top. We did it for, he had 2 children, we did it for both children. We finished doing it for both children, so what do? We set the color of U dot color to equal to black. We are now finished with this node. Okay, great. Now, the Q is not empty. The Q has 2 things in it. Okay, so we pull off the, so here's what we do. DQU, so we pull that off. We're now going to do this. By the way, he has 2 children. Okay, so we're going to look at his 2 children. Okay, for each V member of he, we're going to look at 3 first and then 5, because 3 comes before 5. If v dot color is equal to white, yes it is, color is equal to white, so we're going to make it gray. We make the distance is equal to the distance plus 1, so the distance here is going to be 2. Okay, we're just following the algorithm. Okay, and the parent is equal to 2. He brought him into the thing. Okay, we are now finished. Oh, parent is it. Okay, in QV, so the parent, so we put it in. 3 goes in here. Very good. Okay, and now we do 5. Let's go through 5. Color is white. Yes. Make color gray. Good. Distance is equal to 1 plus 1 is 2. Okay, and parent is equal to 2. He is the parent. We, in Q, we put on 5. Very good. We are now finished with, we did 2's 2 children, 3 and 5. We are finished with that. That's how we make the color black. Very good. Next. Now we pull out 4. 4 has 1 child. Let's do it. The child is white, color is white, so yes, so we make it black. I'm sorry, we make it gray. Then distance was 1 here, so the distance here is equal to 2. The parent is equal to 4. Okay. We in Q7, so we put 7 on the list. Okay. 4 has no more children, so we color it black, and we're finished. Okay, let's go back to, okay, finish. So I'm sorry, 4 had, we put on 7, very good. Color it black, we pulled off 4, I'm sorry, we pulled off 4 before. We looked at 4's children, we color it black, we go back, the Q is not empty, we pull off 3. For each child of 3, 3 has no children, so we don't go, we skip this whole loop. Okay, we color 3 black, and we're finished with 3. Great. Next, 5. Okay, now here's where things get interesting. This is where it's different from a tree. A graph is different from a tree. Watch. Look what it says. We're 5. We pull off 5, we pull off 5, we DQ 5. Now we look at all the children of 5. 5 has 3 children, 4, 7, and 6. Okay, let's look at 4. Is the color white? No, it's not. So we skip this whole thing. Forget it. Next, we look at 6. Is the color white? Yes, it is. The main point is this. We do not consider him to be a child of 5. He is a child of 1. Okay? 1 brought 4 into the tree, not 5. Okay? So that's why, okay, so we're doing that. Okay? We didn't look at that. We're not going to look at him either. We are going to look at him. Let's do 6. 6 is white, so we color it gray. The distance, well, his distance is 2, so his distance is going to be 3. And his parent is going to be 5. Okay, that's very good. Next, we put 6 on the thing. Okay, good. We in Q. Very good. Next, so we now, oh, sorry, we finished 4 as a child, we finished 6 as a child. Now we look at 7 as a child. Is 7 white? No, it's not. It's gray, which means it's been seen already. It was seen by him, so we're not going to even look at that. We're going to skip that. Finish. Okay. Next, 5 had 3 children, 4, 6, and 7. We looked at all 3. 1 was black, 1 was gray. We didn't touch those. 1 was white. We made it gray. Finished. 5 is colored black, and we're finished. Great. Next, Q is not empty. Q is not empty. So what do? We pull off 7. Pull off 7. Okay? Pull off 7. 7 has no children, so we're finished with it. Color it black. Next, pull off 6. 6 has a child, 9. Okay, pull off 6. So we look at its child. The child is white, so we make it gray. The distance here was 3, so we make the distance 4. The parent here, the parent of this guy is going to be this, is going to be 6. Okay, and very nice. 6 has no more children, so we color it black. I'm sorry I didn't put on 9 over here. Okay. We color it black. We're finished with that. Next, we pulled off 6. Already. Pull off 9. 9 has no children. We color it black, and we DQ it, and we're finished. Now the queue is empty. Okay. Notice we did not hit 8. Why? Because we have nothing going to 8. Okay, 8 has things coming out. Notice I did this specifically because we will not have this thing if we did it with an undirected graph. The book does it with an undirected graph. You have to know both ways, directed graph and undirected graph. Okay, and that's the end. Okay, we got all the information we wanted from this tree. Okay, nice. Okay, question. How much work is done? We always ask that question. Okay, initialization is O of V. Hold on. This is O of V. That's the initialization. Okay, and how much work is this? Basically, if you notice, we're going through for each edge. We're going to hit every single edge in this thing. Okay, and so this is O of E. The number of vertices, this is of the order of the size of the vertices. This is of the order of the size of edges. Okay, and for each edge we do a certain amount of things. Okay, so the whole algorithm is O of V plus E. Number of vertices plus the number of edges. Okay. Page 599 through 601 is an analysis of the algorithm, and they show basically that the algorithm works. Okay? Page 601 is a recursive print path, which I want to actually go through. It's a beautiful little algorithm that shows how it does it. But before I do that, I want to show you clearly what the tree is here. See, here's a father, here's a child, here's a father, here's a child, here's a father, here's a child. Okay, here's a father, here's a child. He is not a child through here, he is not a child through here. Here's a father, here's a child, here's a father, here's a child. Here is a father, his father is 4, not this way, but this way. So we have that. Okay. Now, the shaded in edges all form a tree. This is shoot, that's a 2. No, that's a 1. This is distance 0, first generation, second generation. 1, 2, 3 is second generation. We saw 3, 5, and 7, one right after the other, 3, 5, and 7. Okay, third generation, fourth generation. Okay, very, very nice. That's a tree. Okay, he is not in our tree. If you wanted to hit every single vertex, and you do, what you have to do is run this again. And when you're going to run this again, you're going to get distance is equal to 0 because he's going to be your new root. Okay, parent is equal to nil, and he has no children, so there's nothing. He has no children. That he has children, but they've been seen, so he doesn't get that. Okay, let's just do that last algorithm, that print algorithm, because it's very clever. It's a recursive algorithm. And again, this is page 601, so it goes as follows. Print path G, the graph, S, V, V. Print the path from the starting point to V. Okay? It's a clever little algorithm, and I like to go through it. If V equals S, if the place where you finish is the same as your starting place, then print S. Okay? You want to know a path from the starting place to V, the starting place? Just print it. It's finished. Okay? Else, this is your boundary condition. In every single recursion, you have a boundary condition. Else, if parent of V equals nil, if V doesn't have a parent, then there's no way you're going to get from S to V. For example, if I plugged in 8 over here, okay, there's no path from 1 to 8. This parent is nil. Okay, so what do? Print no path. Okay, again, that's kind of like, okay. Else, if the parent is not nil, okay, else print path G, comma, S, the starting point, parent of V. Okay, and when you finish that, print V. Okay, it's a very clever little algorithm. It says as follows. You want to print a path in the graph G from S to V. So if the finishing point is the same as the starting point, just print S. Else, if it's nil, if the parent of V is nil, then just say there's no path. Okay. Otherwise, print. You want to get from S to V. Print from S to the parent of V, and then print V. Let's go. Let's do it. Let's go from 1 to 9. Okay? So here's what I do. I want a path from 1 to 9. So here's what it does. 1 is not equal to 9, so this is not true. The parent of 9 is 6, so I can't write no path because like this. So here's what it says. Print the path from 1 to 6. Okay, fine. Now it recursively calls itself. Okay, you want to print the path from 1 to 6? Fine. 6 is not equal to 1. The parent is not nil. So print the path from 1 to 5. Okay, fine. Now I have to go through this. From 1 to 5, parent of this is not nil. 1 is not equal to 5. So I have to print the path from 1 to 2. Great. You want to print the path from 1 to 2? Parent is not nil, so we go back. Print the path from 1 to 1. The path from 1 to 1 is 1, so print 1. That's exactly what it says. When you finish that, you have to do print from 1 to 2, so then print 2. When you finish with that, you're coming out of the recursion now, you print 5. You finish with that, so coming out of the recursion, you print 6. When you get from 1 to 6, the last thing to do is print V. So you print 9. So the path from 1 to 9 is 1, 2, 5, 6, 9. I like it because it's a clever little recursion algorithm. Great. That takes care of breadth first search. And now we're going to do depth first search. You don't have to watch this. Okay, now we finished breadth first search, now we do depth first search. This is section 22.3, depth first search. Breadth first search used a queue. This is going to use a stack. This uses recursion, which is good for a stack. That used a queue, which was FIFO, first in, first out. This uses LIFO, last in, first out. Okay, so there's a lot of difference. Let's go through what depth first search is. Depth first search means you visit your children's children before you visit any siblings of your children. In other words, go down to all the way down before you visit another child. Okay, so the grandchild goes before the uncle. That's the way to think of it. Okay, this depth first search is used in a lot of different places, including backtracking, which is very important in AI. Okay, and it's used a lot. Okay, we do the same thing here. We have, again, depth first search of a tree. You know that from data structures. But now we do depth first search of a graph. And what we do is we build a tree into the graph, just like we did with breadth first, but it's going to be a different type of tree. Okay, so we create a depth first tree. Okay, so for a given graph, V comma E, vertices and edges, we build V comma E pi. Okay, the same vertices, the graph is going to touch every single vertex, but it's just going to be a subset, and the subset is going to be given by who's your parent, who's the parent. Okay? Okay? Okay, now, we stored, for breadth first search, we stored the color, the distance, and the parent. Here we store something else. For every single node we have v.d, which is the discovery time. When did the algorithm discover it? And v.f, which is the final time. Okay, and final time means when's the algorithm finished with it. We're going to use both of these, but I just remember the same thing also. We're going to have colors for each one of them. This is going to be white, which means it hasn't been discovered yet. This is going to be gray, which means it's been discovered. And this is going to be black, which means it's final. I finished with it. I'm never looking at that vertex again. Okay, and always v.d is less than v.f. Okay. When you discover something, it's before you finish it. If we are not, if we do not hit everything, okay, we're going to have the same problem before. We have a directed graph. We might not hit everything. So we're not going to create a tree. We're going to create many trees. Many trees is called a forest. Okay, and so we do that. Again, I'm going to write up the algorithm and an example. We're going to go through it together. But the algorithm's in the book. Okay, this is the algorithm. It's on page 604 of your book. Again, I strongly urge you to rewrite the algorithm. There's nothing like writing the algorithm and working it out in an example. Make up your own example and you'll see it. Here's an example. This example is similar to the other one, but not really. It's not the same. I added in more edges, and you'll see why in a second. Notice 8 and 9 are by themselves. Once you get from 8 and 9, you can't get, from the other ways, you can't get to 8 and 9. That was done on purpose. Okay? Okay. This is going to be our stack. I told you we don't use a queue, we use a stack here because we're doing recursion. Let's do it. DFS, depth first search, for each vertex set at white, everything's set to white. The parent is equal to nil. We'll put in the parent when we have it. And we have a global variable called time. Okay, time starts off as 0. And it's going to be incremented continuously, and that's where we do our timestamp. Timestamp is as follows. You know, you come into an office and you want to show that you get it, so you get it stamped. There's a little machine that shows, okay, this was handed it and at this and this time. So that's what we're going to do here. But we're going to have to constantly increase that. Great. For each vertex u, member of G of E, if u color is equal to white, DFS visit. That's this. Now this is a recursive algorithm. DFS visit calls DFS visit. This is like an outside thing handling the recursive algorithm. Okay? Notice there's no starting point. In the breadth first search we had a starting point. Here we're going to get a whole forest, not tree, forest of things. Okay? So we're going to start with 1. We're going to visit 1. So let's do it. Now, I am very prone to mistakes. Usually I have students here to giggle whenever I make a big mistake, but here I'm not. So I might make mistakes. So I'm going to look in the paper to make sure I got it right. Okay? Parent is equal to nil. His parent is nil. Okay? Okay, now I'm going to visit with 1. Let's see what we do. Time is equal to time plus 1, so this was 0, this is 1. U of d is equal to time, so we're visiting with 1, so his discovery time, not distance, discovery time is equal to 1. Okay, okay, great. We're going to fill in its final time later on. His color becomes gray. Okay, that means don't visit him again. For each v member of G, that adjacency of U. Look at U, that's U. Look at the adjacency list. Look who's connected to it. So again, 1 has 2 children, 1 and 4, and we have to do the following. Okay, if v dot color is equal to white, it's white. Then v dot parent is equal to U, so the parent is equal to 1. Okay, and then visit v. I'm sorry. So we first visited 1. That was at the bottom of our thing. And now we're going to visit him. Did I make him gray? We didn't make him gray yet. Okay, so we didn't finish 1, and now we're going to visit v. Okay, so now we're here. Great. Let's do with that. Time is equal to time plus 1, so this becomes 2. Okay, color is equal to gray. He becomes gray. Sorry, u dot t. His discovery time is 2. Okay, good. Did I tell you who his parent is? No. We made him gray. So let's do that again. Time is equal to time plus 1, so that's 2. His discovery time is 2. His color is gray. And now we go for the children of 2. This is what we say. You'll go for the grandchildren before you do the siblings. So before we come to 4, we're going to go to the grandchildren here. Okay, so let's go through it. He has 2 children, 3 and 5. We're going to do 3, because 3 comes before 5. So we're going to visit 3. Very good. So now we're visiting 3. So, I'm sorry, we put in 2 over there, and now we're visiting 3. That's good. Great. Let's do this. Time is equal to time plus 1. That's a 3. U of discovery time is equal to 3. That makes sense. Color is gray. Color is gray. Very good. For each child of V, okay, we're looking at 3. 3 has no children, so we skip this whole thing. Skip this whole thing. 3 has no children, and there's nothing coming out of here. So we skip this whole thing. Then look what we do. Color is equal to black. Time plus plus. I used a little C++. The book does that. So this becomes 4. Okay. U dot F is equal to time. F, that's the final time. When did this become black? At 4. So we discovered this node at 3. And we finished it at 4. Why? Because it had no children. Okay, and if it doesn't have children, we don't have to go further. Okay, so again, depth first search, you go to children, children, children until you can't go anymore. Well, if you don't go anymore, then the discovery time and the final time will be 1 apart. Great. I am now finished with 3. Because 3 is, I have finished this thing with 3. Now I'm back at 2, and I'm looking at 2's children. One of the children was 3. Yippee, we did that. Now we're going to do 5, another child of 2, which is 5. Okay? So, for some odd reason, I'm missing out. I'm sorry. When I did 3, I left this out. So, parent is 2. Here we have parent of 1. Okay, great. So let's do it. So now I'm going to visit 5. I'm sorry. So we're now here. Color. We're visiting 2's children. We visited 3. Now we're visiting 5. For each vertex, if color is equal to white, it's white. Then parent is equal to U. So its parent is 2. Very nice. DFS 5. Let's go visit 5. Okay, so now we go visit 5. So I have to put this in here. 5. So far so good, didn't make a mistake yet. Okay, so good, now we're visiting 5. Okay, let's just fix that up a little bit, because that doesn't look right. Okay, he goes here. His vertex is 5, his parent is 2. Okay, now we come here. Oh, I'm sorry, I didn't increment the time, so his time was 5. Oh! Great, I'm sorry. So fine. Time is equal to time plus 1, that's 5. Discovery is 5. So not only is he 5, he is 5, right? So far so good. Okay. Color is gray, we make him gray. And now we look at all the children of 5. Children of 5. Let's see, how many children does 5 have? He has 1, 2, 3, 4 children. Okay? We're going to look through them in order. Okay? So the first child is 3. So now we're looking at 5's children. Now we're looking at 5's children. So 3. If color is equal to white, no. Color is equal to black. So we leave it alone. Okay? Next, what other child does 5 have? Answer, 4. We do this in numerical order. 3, 4, 6, and 7. So 4. Let's do 4. You ready? We're going to visit 4 now. Let's go through it. Color is white. Yes, it is. So make his parent equal to 5. Good. Okay. And now we're going to visit 4. Very good. We're here. We're now going to visit 4. I'm sorry, we visited 4. We made the parent there. Now we visit 4. Okay, time is equal to time plus 1, so this becomes 6. Hopefully. Okay. Discovery time is 6. D is equal to 6. Okay, good. Next. Color is gray. We make him gray. Okay. And now we look at children of 4. Okay. 4 has 1 child. 4 has 1 child. Color is white. We make the parent equal 4. Okay. And now we visit 7. Okay, great. Now we visit 7. So we go up here and we visit 7. So, let's visit 7. 7, we're lucky. 7 has children. 7 has children, but not white children. So we do this. So let's do it. Time is equal to time plus 1. This becomes 7. D, we're visiting 7 now. So D is equal to 7. Color is gray. Color is gray. Now we look at each one of the children of 7. So let's go through it. 7 has only 1 child. We look through that child. It is not white, so we don't do this. We are now finished. We only had 1 child. We did not do this. We now make 7 black. We increment the time to 8. We set the final time as 8. And I still didn't make a mistake. That's amazing. Great. Okay. But I did leave this out. So let's do this. 5. I'm sorry. We had a 4. We have a 7. Okay. So we just visited 7. 7 had no interesting children. And so we're finished with 7. Okay. So when we colored 7 black, we are finished with 7. Okay. We pop 7 off. And we're now going to finish with 4. Let's go through 4. 4 had, I'm sorry, should have looked at this, but this was busy. This was the only white child of 4. We are now finished with 4. 4 has no other children. So what do we do when we finish it? We color it black. We increment the time to 9. We set the final time as 9. So far, so good. Didn't make one mistake yet. Excellent. I am now finished with 4. We're back at 5. Let's just remember what we had by 5. 5 had 4 children. 3, 4, 6, and 7. We visited 3. We visited 4, which gave us a little time to visit 7. Now we're back to 6. So now we're going to visit 6. So let's go through it. So we visit 6. Let's see what happens when we visit 6. We increment the time. So this becomes 10. We set the discovery is 10. Okay. We color it gray. Now we visit the children of 6. 6 has no children. 6 has no children. There's something wrong here. When I visited 6, I didn't put down the parent. The parent is 5. Okay, so that works out. Sorry. Okay, so we finish. 6 has no children, so we skip this. We set the color to be black. We increment the time to be 11. We discovered 6 at time 10. We finalized at time 11. That's because he didn't have children. Okay, and we are now finished with 6. Great. We're still back at 5. Okay, we go back to 5. 5, let's go through it again. 5 had 4 children. 3, 4, 5, and 7. 3 was already visited. We visited 4. From 4 we went to 7. We visited 6. We are now finished all the children of 5. What do we do when we finish the children of 5? We color it black. We increment the time to 12. We set the final time as 12. So far so good. Okay. Final time is 12. We are now finished with 5. We go back to 2. 2 had 2 children, 3 and 5. We did 3 right away. We did 5 and we visited everyone else. We are now finished with 2. Guess what we do? We cross out 2. We increment the time to 13. The final time is 13. Here, great. Okay, we are now finished with 2. 2 we cross out. We're back to 1. 1 had 2 children, but we met this child while visiting this child's children. Okay, so he is not a child of him. He's a child of him. Parent is 5, not 1. Anyways, we are finished with 1. We increment the counter to 14. We set his final time to equal to 14. Okay, so we discovered him at 1 and we did everything else at 14. We finished everything else at 14. Great. We are not finished because we have to do this. We are not finished because we have to do this, but we're finished with this. Okay? Great. So now let's do this. Okay, I'm just going to give you the answers to this because I want to do this a little bit quickly. We're a little bit bored with this. This is discovered at 15. This is discovered at 16. This is finalized at 17. This is finalized at 18. Okay? And his parent is 8. And his parent is 0. Okay. And I am now finished. Okay? Okay, that does it. Okay, I didn't finish with the time over here, but that was my global variable. We're now done. Everything is done. Everything is black, and we're done. Got all the information. You're going to see the way we're going to work with this information in a minute, but this is very nice. Great. I'm going to erase this now, and I'm going to describe the book does something very nice now. it makes 4 types of edges. It classifies all the edges in this thing into 4 classes. Okay? And the book does it formally, gives you an exact definition. I'm going to be a little bit less exact, okay, but I'm going to give you the intuition more, and you're going to read it on your own. So there are 4 types of edges. There are tree edges. There are back edges. There are forward edges. And then there are cross edges. So let's just do tree, back, forward, and cross. Okay? Now for each one of them, you're going to have a vertex U and you're going to have a vertex V. Okay, so let me just tell you here. Here, U is a father of V. Okay? If it's in the tree, that means U is a father of V. I'll fill in this in a second. Okay? Here, U is a child of V. It's going backwards, you'll understand in a second. Here, U is an ancestor of V, and here U and V are in different trees, or are not ancestors of each other. So you're in one of these if you're not. Okay, let me just show you and you'll understand it perfectly. Let's do first the trees, because this is the most intuitive. His parent is him, so he's in the tree. His parent is him, so he's in the tree. This edge brings it into the tree. I should really shade in these edges. Okay. His parent is his parent is him, so he's in the tree. Let's go on. His parent is him, so he's in the tree. His parent is him, so he's in the tree. He's in the tree. He's in the tree. He brought him into, so he's in the tree. Okay, great. Now, let's go through this. Let's do back edges. Don't like to do back edges. Okay, ready? I'm sorry, I should use a... descendant. U is a descendant of V. I want to show you that this is a... I'm sorry, let's do this. Back edges. Look at him. He had a child here. He had a child here. Now, he is a grandchild of him. So we say, U is a descendant of him. So I'm going backwards, back like that. Okay, so he's a back edge. Who else is a back edge? He had a child, him. He has a child, him. This arrow is pointing back to his grandfather. So this is a back edge. We'll talk about this in a second. That's not a package. Okay, let's talk about this. What's this? He has a child, him. He has a child, him. He has a child, him. So he is pointing to his great U is pointing to, he's an ancestor of V, so he's pointing forward. Okay. Backwards means you're going back previous generations. Forwards means you're going down forward generations. T means you're going forward just one generation, which is what we're looking for. Great, let's do this one. He is not a descendant of him. Well, he has no descendants, and he is not a descendant of him, but they're not in different trees. They're both in the same tree, so this is a cross edge. Okay? Or are not ancestors of each other, so that's a cross edge. Let's do this. He is a father of him. He's a father of him. This is a forward edge. This is a forward edge. He is a father of him. He's a father of him, so he is looking down at his grandson, so that's forward. Okay? Let's do these. All three of these are different trees. Here's one tree, here's the other tree. They're not ancestors of each other, they're different trees. So this is a cross edge, and a cross edge. Okay? Now, these classifications are used all over. They're used especially in AI. When you're searching for things, you have to keep track. Are you going backwards? Are you going forwards? Etc., etc. So this is very important in AI. And I think I have all the information. The book gives exact definitions of when, in terms of discovery time and final time, how these things work. But I gave you a good intuition. You just have to see that the book's definition matches up. So that takes care of that. Okay? So this is very nice. Okay? The book also has a beautiful way of describing this thing, these things, and I'd like to show you for this example how it looks. Okay? I'm going to erase for a second, and you don't have to spend time watching me. Okay? This is a beautiful way of seeing the results of this thing. Okay? 1 through 18 is the time. You discovered number 1 at 1. You finished him at 14. In that time, you discovered child number 2. Child number 2, you discovered 3. Remember, 3 had no children. 5 and 5. So 2 discovered 3 and 5. And here's the starting point, and here's the ending point. It was discovered at 5. It was finished at 12. 5 had 2 children, 4 and 6. 4 had 1 child, 7. Okay? Then we did this a little bit quickly. 8 was found at 15 and discovered at 15 and finalized at 18, and he had 1 child, 9. Okay, so it's a nice way of visualizing how this algorithm works and how it finds it doesn't finish things until all its children are found. Great. So that takes care of that. Next, section 22.4 is uses this depth first search to do something very nice and important. Okay? So section 22.4 is called the topological sorting. Topological sorting. I'll explain to you what that's all about. Okay? Okay. So I want you to consider the following thing. You have, let's use a better color. Consider the following thing. A, B, C, D. No good. They're all no good. Getting to the end of the semester. Okay? Okay, and they're set up like this. A goes to B, A goes to C, B goes to C, D goes to C. Okay? set up like this. Now, what we want to do is we want to rearrange this graph. Now, a graph, again, you can change the way a graph looks. A graph is about connectivity. It doesn't matter how you arrange the nodes, as long as you put it away, put it nice. So you want to twist the shape of this graph so that the nodes are all straight. Okay? And what it gets is as follows. I can do that. I have A over here, B over here, D over here, and C over here. Okay? And now I'm going to do it like this. A goes to B, that's that. B goes to D, that's that. D goes to C, that's that. But we have other things also, because I have A goes to D, and I have B goes to C, and I have A goes to C also. Okay, so I rearrange this so that it's in alphabetical, not in alphabetical order, I'm sorry, so that all the arrows go one way. Okay, and we're going to do this a lot. We're going to do this nicely. Okay, well, let me just tell you where this gets used. Okay, let's think about getting dressed, and I'm thinking as a man getting dressed. Okay, you have to put your undershirt on before your shirt. Okay, now it doesn't matter when you put your watch on in terms of your undershirt and your shirt. Okay, you have to put your underpants on before your pants. You have to put your pants on before you put your shoes on, but you can put your socks on before or after you put your pants on. So that's an interesting thing. Okay, now what you do in real life is linear time. It's straight. So you're going to do one of these things first before you do other things. Okay, but you have to make sure it's straight. Okay, so what we're going to do is we're going to make a graph into a straight line like that, where all the arrows are pointing this way. Let me give you a more practical example. I'll go again. That is very practical. You somehow have in your head a built-in list of prerequisites of what you can't put on your shoes before you put on your pants. Okay, you can't put on your pants before you put on your underwear. Not your undershirt. You can put, but that's, I don't want to get off color here. Okay, great. Let me give a more practical advice. There are a lot of computer science classes, okay, and you have all these prerequisites of we can't do one before the other. But you yourself make a list of what you'd want to do and how you're going to do it. Okay, you go on Professor Langzim's door. There's a whole big complicated diagram of what's a prerequisite for the other. But what you do is you make a list like this, so that has all the things of what you're going to do one after the other. Great. Now, what we're going to do is, given a graph, we're going to make such a straightforward thing using the DFS. So let me show you the algorithm and let me show you the example using the example that we did. You don't have to watch it. Okay? So we're going to topological sort something. We're going to do the example that we did. Okay? So let's just read it. Topological sort of G. This is in the book, page 613. Call DFS of G to compute final times v.f for each vertex v. As each vertex is finished, insert it onto the front of a linked list. Return the linked list. Okay? So if you looked at the way that was done, we had the following. Okay? I had the vertex 3. I'm sorry, my linked list is going to go like this, but the first thing I put on is going to be here. Then I'm going to put this, then I'm going to put this, then I'm going to put this. You're going to see it going up. Okay? Let's just remember the discovery time for vertex 3 was 3, and then we finalized it at 4. I'm going to write it like that. Okay? The next discovery time, the next vertex that we finalized, we found this at 7, and we discovered it at 7, we finalized it at 8. The next thing was 4, okay? Okay, and 4 we discovered at 6, and we finished at 9, Okay, notice this is increasing, 4, 8, 9. Okay, next was 6, vertex 6, which we discovered at 10, and we finished at 11. Next was vertex 5, which we discovered at 5, and we finished at 12. Next was 2. Okay. By the way, this has a feel of that greedy algorithm where we look at the final times. Notice the final times are increasing. 4, 8, 9, 11, 12. 2, which we discovered at 2 and finalized at 13. And finally 1, which we discovered at 1, but we finalized at 14. Hold on, we're not finished. Okay? Because we had 9, which we discovered at 16 and finalized at 17. And we discovered 8, which we discovered at 15 and 16. Okay. Now, there's an arrow here. There's a tree arrow here. There are also tree arrows here. 2 to 5. These are all tree arrows here. There are also forward arrows here. Back arrows would go backwards. Okay, so we don't have back arrows, but we have forward arrows here. Okay, but the main point is you can do this first and you can do this. By the way, this whole thing can go over here also, and you wouldn't be in trouble. But you can do this, you can do this, you can do this. So this gives you a forward way of taking your tree and stretching it very nicely. Anyways, that's the end of our elementary. You have to read more about that. Okay? There's also section 22.5, but we're not responsible for that. That's finding components. There are many, many different things you can do with this information. I just want to give you a basic introduction to it, but we're not really going to go through every single section in 22.5. Next time we do every single section in section 22, in chapter 22. Next time we do 23, and then we're going to do, well, we'll see what we do then. Okay? Graph algorithms are absolutely pretty and worthy of study. Take care.